This is a short video about 2.1.2 of Stein's elementary number theory book, and we are building towards what's called Euler's theorem. So the first thing we'll look at is, that's not a highlighter, is Euler's phi function. By the way, some people say phi, like I do, some people say phi, it doesn't matter, say whatever you're comfortable with. So I'll say phi. So what is Euler's phi function here? So it's the following: for any natural number, phi of n is going to be the cardinality of the following set. So the set of all natural numbers that are less than or equal to whatever that n is, whatever the input is, that are relatively prime to n. So for example, phi of 1 or phi of 1, whatever you want to say, it's the cardinality of all natural numbers that are relatively prime to 1. It's just 1. It's just one thing in it. Similarly here, the numbers that are relatively prime to 2 that are less than or equal to 2, well, 1 is the only possibility, and that set has one thing in it. Now you see the natural numbers that are less than or equal to 5 and relatively prime to 5 are 1, 2, 3, and 4. And so how many things are in that set? In this case, 4. And maybe just one more example. The numbers that are relatively prime to 12 that are less than or equal to 12 are 1, 5, 7, and 11. So phi of 12 would be how many are in that set, which is 4 again. Now there are some patterns. So if you take any prime p, well then the number of natural numbers that are relatively prime to p, well, think about it. Any of the numbers before p, they can't divide p, otherwise p wouldn't be prime. So in particular, well, there are 1 through p minus 1, so p minus 1 numbers that are relatively prime to p. So in general, when you take Euler's phi function of a prime, you always know it's p minus 1. Whereas something like trying to find phi of 12 is a little bit harder. We have to kind of list them out. Now there are some interesting properties of this function phi itself. And the first one we'll look at in a little bit more detail is if you took two numbers m and r that are relatively prime to each other, well, this property over here, over where, I'm trying to get away, I'll just do this. This says that phi, that product, phi of m times r, could equal phi of m times phi of r. I just caught myself. I said in the beginning I'll say phi, and I say phi most of the time. I'm not sure which one I say more often. So anyway though, more importantly, whether I say phi or phi is, phi of m times r can split as phi of m times phi of r as long as m and r are relatively prime to each other. And what we'll see is that that property yields a nice way to compute what phi of n is, as long as I know maybe the prime factorization of n. So maybe to give you an example, phi of 15 is equal to phi of, I could think of 15 as 5 times 3, and by this property here, since 5 and 3 are relatively prime, I can use this to split this as phi of 5 times phi of 3. Now what can I do? Well, 5 and 3 are primes, therefore I could use this formula here, that phi of a prime is just one less than the prime. So this should be 4 times 2, which is 8. So just to check that, Sage has Euler's phi function built into it, and they do an example. Euler phi of 2007 is 1,332. So what you should read that as is there are 1,332 natural numbers that are less than or equal to 2007 and are relatively prime to 2007. And just so that you believe me with my computation of phi of 15, if I say Euler phi of 15, I'm supposed to get 8, according to what I did by hand. And Sage agrees with me, so that makes me feel good about life. So now what we'll do is we will present, again, the main result of this section. So what is Euler's theorem here? So if you take any element x, or any integer x and n that are relatively prime to each other, that's what this GCD business says, then this says that x raised to the power of phi of n should be equivalent to 1 mod n. Now, it says the proof starts here, but the proof actually doesn't really start to the next page. This is more of a modern algebra kind of interpretation of what Euler's theorem tries to say to us. Before I dive into that, though, it might be good for me to also mention here, doing computations with modular arithmetic has some tricks in it. And it has some tricks to make it easy to do. And you remember maybe in the first section about chapter 2, we said that we're going to do crazy things like, maybe compute the first 100 digits of like a multi-billion digit number. How do we do that? And it's through little tricks like this, like Euler's theorem, that gives me something to build off of. And we'll see this a lot when we get to the encryption section later on in the book. And so anyway, though, to get back to this here, what is Euler's theorem trying to say as far as groups go? So remember, z mod nz star is the group of units of z mod nz. In other words, take all the equivalence classes that are relatively prime to whatever n is. And in that case then, if you were to count them out, well, there should always be phi of n things in that group. So to give you an example here, z4, or well, that's how we'd write it in a proofs class, say. It's how I used to write it. But now we're looking at z mod 4 z star. Remember, that's equal to, I'm going to write it as 1 and 3. Those are the only two things in that group. And what I'm saying is, how many things are in that group? It's 2. And what does 2 also happen to be? 2 also happens to be phi of 4. So the point is phi of 4 is the order of this. And in general, z mod nz star has order. In other words, cardinality for group here has order phi of n. It's whatever that n is. So maybe it's a little hard to see. So that's important for us. And remember, maybe in the previous video, we mentioned something that was called Lagrange's theorem in group theory. And what it said is that the order of an element has to divide the order of the group. And so this is essentially what Euler's theorem says to us, is that, again, the order of an element of z mod nz star divides the order of the whole group, which is phi of n. So this isn't trying to say that the order of any x is phi of n, but we're saying that whatever the actual order of x is has to divide this number here. And we'll look at some examples a little bit later. And again, this is a special case of, again, Lagrange's theorem here. But now maybe what's the proof of it as far as our class goes? So what we're going to do is we're going to note capital P as the following set. Take all your natural numbers that are between 1 and n inclusive that are relatively prime to n. So in other words, if I was in z mod 4z, right, I'm saying the a's I'm going to use are 1 and 3 from what I was doing, well, I guess I erased it, from what I was doing earlier. So just kind of take the natural a's that you'd use to represent equivalence classes, and but I only want the ones that are relatively prime to my n. And so now what we'll do is, well, if you took any element, any x, and multiplied it through your set P here, what do I have? I should have that their product, all the x times a's multiplied together, remember what that is, for every a in my set P, should be equal to just the product of the a's themselves. And because these things are products of the same numbers mod n, remember those products just start to repeat because this is a group under multiplication. In other words, we're always closed under the operation, so I should get the same result at the end. So now if we think about what can we do, I also know that it happens to be highlighted for me too. Maybe I'll highlight some more. I know that a and n are relatively prime to each other, and remember that's the condition to cancel out a's. And so what do we get then? I would cancel out all the a's, and then what do I have? Well, how many times do I multiply x to itself? Well, this says you're going to multiply however many times, however many factors you have in P. So in particular, this says you would have x raised to the however many things that are in P power. That should give you, when you cancel the a's, all the a's individually, that should give you 1 mod n. So just to say, what if your P had I don't know, 2 things in it, say, then you would have something like x times a1 times x times a2, and that should be congruent to just a1 times a2. And what do we have? What are we trying to say? I'm saying that because these elements are relatively prime to n, so I guess I should say mod n at the end, that's how I get 1. And how many powers of x do I have? That's where I get x squared. And what is that 2? That 2 is, well, how many a's do I have? Again, that is what this and this are trying to say in maybe a small little example to work through what the notation is. And of course, that says that, okay, well, x raised to that many things gives me 1. Finally, though, what is P? Well, P is the set of all my integers between 1 and n that are relatively prime to n. Remember, that's exactly the number of things in that set is phi of n. So cardinality P is phi of n. And that's Euler's theorem. So again, we just came up with this formula. So we can do some of this in Sage to illustrate how it works again. And then it also, there's maybe a more convenient way to establish an element, an equivalence class, mod n. And so the convenient way to do it is this command, mod with a capital M, x comma n. And so in particular, what does that do? That just automatically spits out the equivalence class of x and n. So if you watched the previous video, we had another way to do it, which was to set the ring you're working in, and then this command specified I want A to be the equivalence class of 3. But now what we're saying that we could do is I could just do mod, I could do 3, 10. That's a quicker way to do it. And again, that's what this is saying right here. And so what is this little block of Sage code trying to do for me? So if I took n to be 20, so I'm in like z mod 20z, I'm going to set k to be whatever phi of 20 is. And if you compute phi of 20, you should get 8. There are 8 numbers that are relatively prime to 20 that are less than or equal to 20. So what are we going to do? If I took every element that is in z mod 20z star, again, how do I get that star there? Because I've specified that x and n are relatively prime. I only want their equivalence classes that are relatively prime to 20. If I took each of those elements and I raised them to the 8th power here, how do I know that's 8? Because that's k. What should we get? Well, we should get 1 every time, right? If I look at Euler's theorem, this says that x to the 8th should always be equal to 1 mod 20. And because that 8 is phi of 20. Euler's theorem predicts that that should happen. And all this Sage computation is trying to do is very quickly, if you raise each element of z mod 20z star to the 8th power, you get 1. And that's all we wanted to verify here.